All right, so I'm grateful for this opportunity to give you an overview of my work on shape representation and a few other related topics. Kind of somewhere in between the kind of neural representation that we've been talking about and some of the more mathematical approaches, and I think there's some middle ground, which I'm not exactly in the middle of, but we try to connect some of those things. So, I mean, we talked a lot about shape today. I'm not sure I've heard anybody actually give what mathematicians or some statisticians have actually given as the classic definition of shape, which is sort of every property of a set of points or a contour that is invariant to scale rotation and position shape. So that's a traditional definition which just encompasses every aspect of a contour. It's not super useful for a perceptual psychologist because obviously the visual system is going to represent or be interested in certain aspects of form, not other aspects of form. And so that's what I mean when I say what is the shape. So in the perceptual literature, a huge number of geometric aspects of shape, like the shape of the cell, have been proposed. I'm just going to give you a partial list here. Curvature extrema, which is related to what Anita was just talking about, with points on contour that are relatively sharply curved, either convexly or concavely. Shape codons, which is a qualitative assembly of elements like that. Shock graphs, which is related to what I'm talking about. Neural population codes, and various other things. So some of these, I want to say, I don't want to make it sound like there's a billion things that have been suggested. I'm going to try to sweep them all away. Some of these are closely related to what I'll be talking about, and some of them are closely related to each other. And some of these are kind of overlapping. The one I want to focus on is the last one here, medial axes. So medial axes are an idea which is motivated by some of the considerations from group theory that we heard this morning. So I'll try to make a bit of a connection. Just to motivate it a little bit, this is a famous demonstration by David Marr of kind of what it takes to recognize things in terms of shape. And it's a very dramatic demonstration. So if you've never seen this before, Marr made these pipe cleaner animals. And I mean, can everybody recognize what that animal is? Right? It's a giraffe, right? Even though it's actually a pipe cleaner. And what's this? An antelope or something like that. Rabbit. An ostrich, I suppose. And so the point that Marr was making was that these objects don't really resemble the real objects in a lot of ways. They don't have the same color, the same texture. They don't actually even have the same shape in the usual sense of the word, meaning they don't have the same outer boundary. But what they do have is that axial structure. And so Blum, who I mentioned, wanted to expand on that idea. So the medial axis transform is a geometric idea that's really a generalization of the idea of symmetry and variance that we learned about this morning. So basically, the medial axis transform is I don't really have a definition on the slide, but the medial axis transform is a local symmetry representation of an object. I'll give you some examples. So the medial axis transform is technically the set of points which are the centers of circles that are maximally inscribed circles on the shape. So what it basically means is, from the point of view of the contour of the shape, the points that are local axes of symmetry. So for example, this point is a local axis of symmetry between this side of the shape and this side of the shape. So it's a local bilateral symmetry. And of course, here in the middle of the shape, it's symmetrical between the top and the top and bottom. So it gives you something like the skeletons that look like the pipe cleaners, but as you can see from this example that Feldman himself demonstrated, not really. So subjectively, you might say that the skeletal structure of a rectangle is just like a horizontal axis, but what you actually get with the medial axis transform is something that is forking at the ends. And from a modern perspective, a kind of more general way of saying this problem is that the medial axis transform is very sensitive to noise. So again, some of these demonstrations are from Blum himself, who's very well aware of the limitations. But so, for example, you take a little bite out of the rectangle, and the medial axis transform kind of goes haywire. So it's still correct, meaning that around these points, the shape is locally symmetric. Around these points, it's locally symmetric. But you get this very non-intuitive structure over there, and if you add noise to the shape, it just goes crazier with lots and lots of spurious axes. And if you take a naturalistic shape like the elephant that I started with, you get, depending on the resolution that the shape is taken, you get lots and lots of spurious axes. So if you're trying to think about this as like the pipe cleaner structure, it's a long way from actually playing that blunt in terms of recognizing the shape or anything like that. So Manish and I have tried to turn this problem around to think of it the way that a lot of visual perception thinks about things nowadays, as as an estimation problem. So I'll give it as a Bayesian estimation problem, but that's not really the point. It's an estimation problem, which means that we're going to think about the shape as data. Instead of thinking about it as an idealized geometric object, we're going to think about it as a set of data that potentially has noise. And typically, in real images, does have noise. And a skeleton, which is going to be something analogous to the medial axis transform but different, is a model of the data. So we're trying to explain the data as well as we can with a model. And so basically shape representation then becomes the problem of finding the best model for the data, which is a pretty general statement of statistical inference in general, but it's not kind of typical in the history of the shape literature to think about shape itself as something to be estimated. So let me explain how the model works. So it starts from an analogy with like simplest kind of estimation problem. So let's say you have some data which are just dots in plane, like the green dots here. And to a statistician, a model of that is something like an idealized distribution with a mean, like the red dot in the middle is a mean, and then there's some random deviance that's sprouted in all directions randomly. And so we can think of those data points as having been generated by a mean with some random deviance. That idea goes back to Gauss, who first thought about statistical estimation in this way. So what we're going to do is to take that point and extend it to a whole axis. And so this sort of breaks one of the symmetries of the point. It's no longer going to be rotationally symmetric, and now it extends it in the plane. And this is what we think of as an axial model. But the idea still is that there are random deviates coming off from it, but now they come off laterally instead of in all directions. But there's still some random elements of the directions they come off in, but they come off to the sides. And then we can do various other things, like we can bend the axis, and then we have random deviates coming off from the bent axis. And then at the end of those deviates, we have little shape elements, which could be the edges, like from the canny edge detector that I need to mention. Other things that we can do to make this a little more general is to branch recursively. So instead of having a single axis, we have multiple axes, and then we get branching shapes. But again, it's the same idea that the sub-axes also generate deviates laterally, and then at the end of that, you get all these edges, which then together are the shape. So the idea is that the red skeleton is the generator for this shape. So in the forward direction, the way Bayesians use the term, the forward direction, the red skeletal model generates the shape. In the inverse direction, we start from the shape, and we want to estimate the skeleton. We want to figure out what skeleton generated it. That's the basic idea behind underneath like everything I'm going to talk about for the next 25 minutes. So to do this in a Bayesian fashion, what you want to do is to adopt a prior and likelihood model in order to just quantify the plausibility of various skeletons or the plausibility of various shapes conditioned on the skeleton. If you're not familiar with Bayesian models, I'm not going to explain it from the ground up here, but that would be a whole separate talk. But for our purposes, that means we have a prior on skeletons, which I'm not going to give in formal terms, but basically favors simple skeletons, like smaller numbers of axes, with less curvature. So a simple straight axis is the simplest thing, and then the more it bends and the more it branches, the lower the prior. And a likelihood model, which is the part about the shape condition on the skeleton. So there, the idea is that this shape has relatively high likelihood condition on this skeleton, but this one has relatively low likelihood condition on this skeleton. This doesn't really fit. So the likelihood model, as with all Bayesian models, is an expression of the degree of fit between the model and the data, so here between the shape of the skeleton. So basically what we want to do, boiling it all down, is to find the skeletal model that maximizes the posterior, which is proportional to the prior and the likelihood, and that's what we call the map skeleton map for the maximum-posterior axis.
Is this all only for 2D?
So, well, I'm going to talk about 3D a little bit later in the talk, but so far everything is defined as 2D. So the map skeleton is the maximum, is the skeletal model that fits the data the best, fits the shape the best, while also being as simple as possible. Now, for those of you familiar with Bayesian models, it's really not a great idea to just choose the map. That's a problem we worry about, but for the rest of the talk, most of them are talking about just choosing that best model. So let me give you some examples. So if you have a simple, roughly elliptical shape like this, you get a simple axis, like a one axis. The solid, the thick green line there is the skeleton, the axial model, and the thin green lines are the random deviates. We call them the ribs that connect to the bone, to the skeleton. But that just shows how the model corresponds to points on the shape. That's not part of the skeleton. It's a single axis model. And then here, if you have like a intuitively two-part shape, I mean, again, these are very simplified shapes, but intuitively that shape has two parts. You get two axes in the skeleton. And I should say the color coding is meaningful here, meaning that the estimation procedure has figured out what the branching structure is. It thinks that these points up here in red are explained by a different axis than these points down here in green. So the color coding of red versus green doesn't mean anything. There are different parts. So it means that there are two parts. And these are all real, math estimates that I'm showing you here. As you get more and more parts, it continues to give an approximately intuitive part decomposition, which is the goal. So again, these are, and here we have multi-part shape that essentially corresponds to what we think, meaning that there's isomorphism between the axes and the intuitive parts is there in contrast to the medial axis transform where it wasn't. So a few more slightly realistic examples. It doesn't always work beautifully, but you can see that in each of these animals, there's approximately a one-to-one correspondence between intuitively the limbs and the head, et cetera, and the color coding, getting the branching structure that the procedure estimated. And a slightly more involved example, here's the original elephant, which gives you a nice axial structure. And here's the same elephant with some noise added. We talked about invariance to noise before. And here you don't actually get the same skeleton, but it's qualitatively very similar skeleton. And if you add a lot of noise, again, it's not quite the same skeleton, but you can still get a very good result. So essentially, this is explaining data with more noise in it, but it still gives the same qualitatively the same Okay, so just to expand a little bit about what I've been saying about part decomposition. So the whole point here is that this is a part decomposition of the shape, which is a whole problem in and of itself. I should say that there is a whole history about the psychology of how people decompose shapes into parts, which we're trying to subsume a little bit here. So I'm not going to give you a whole review of the literature on this, but there's several famous proposals for part decomposition. One is the negative extreme of curvature, likely to be part boundaries, so like the cusps in between the legs and the cusp over here are relatively likely to be part boundaries. And that's certainly true on average. But notice that in our shape decomposition, we sort of explain that fact without actually taking advantage of it. Meaning, there's no point in the computation of the shape skeleton where we actually computed curvature. It's just a side effect of the estimation procedure that there tend to be color changes and part changes near minimum curvature.
Question about, like the elephant in particular, like how much does a human's labeling, like if you take someone who's never seen an elephant and show them this outline, will they, there's some sort of thing about how do we like segment just new shapes, but then there's another which is like, okay, I recognize it as
it's hard to find people that have never seen elephants, but but I mean, studies have been done. Johann Bachman's did one where you get people essentially nonsense shapes and ask them to label the parts and label the part boundaries. And the answer is it's complicated, which is part of why we're trying to come up with a simple principle.
Right.
Meaning they do tend to respect negative extrema. They do tend to respect some of the other heuristics, but there's no magic answer. Every heuristic that was ever proposed in the psych literature, there was some empirical support for this. Meaning either people are doing 10 different things at once, or all of these things are side effects of some common principle, which is what we're trying to.
Okay, cool.
I mean, I should say negative extreme of curvature is kind of our favorite theory in the lab because that idea was from Hoffman and Richards. Richards was my PhD advisor, and Hoffman was Manisha's PhD advisor. So this is like the in-house, dragon we had to slide. But but anyway, I'm not saying it's wrong. I'm just saying it's correlated with this estimation procedure. So another proposal that was actually Manisha's originally was this idea of shortcuts, which is that you tend to cut parts off from the whole in a way that is you use as short distances between negative extrema as possible. So like you don't join this negative extrema with this one over here and cut off all the legs together. You cut off you make cuts that are short. And you can see that's also true in our estimation, although of course we don't compute the length, not directly compute the length of those cuts anymore. So the idea is that these things are just side effects, and that's the spirit of all of this. I'm not saying it always works, but the idea is that we have some central principle that explains a bunch of known phenomena as side effects. Okay, let me say just a tiny bit about the algorithm. It's not an algorithmic theory, meaning that the algorithm is just a way for us to figure out what the predictions of the theory are. not claiming any psychological reality to the algorithm, and we're always trying to come up with better algorithms without changing the basic computational proposal. What we actually do is we use the medial axis transform as an initial proposal that we prune branches based on a Bayesian test. In other words, we basically ask whether each branch explains the data more than it costs in prior penalty. And if it's worth it in terms of the prior penalty, we include it, otherwise we cut it. And then you end up with, with a sort of pruned version of the map. And then we can optimize parameters using a procedure like expectation maximization. It's not a very fast procedure. It takes about 10 seconds per shape on a laptop to show you what I'm doing. I'll show you the examples that I've used. And like I said before, we really do want the full posterior, so this is just a very kind of simple sheet to get to the map. Okay, let me say one more thing about the general procedure before I move on to kind of generalizations. Because this is true of almost every Bayesian theory, I find it particularly cool in the case of shape. Because the map skeleton maximizes the posterior, which is here, this is the posterior being proportional to the likelihood times the prior, it minimizes the minus log posterior, which I've just taken minus logs, left off minus sign, which is what's called the description length in the statistics literature and nowadays in the quantified science literature. So what that means is that the map skeleton is not only the maximum posterior, it's the simplest explanation of the data in the sense that it's the simplest combination of the minimum combination of the complexity of the model with the complexity of the data given the model. And that's the so-called MDL criterion for picking models. And what we like about it is because the idea that we're minimizing some sort of complexity ties it up with a whole huge literature on Gestalt, perceptual grouping and perceptual everything rules, where the idea is we're trying to maximize the simplicity or coherence of the perceptual interpretation. Of course, the Gestalt is, Prägnanz, if you've never seen this literature before, it's just a German word that means something like goodness of form, and it's usually not translated because nobody knows what it means. Nobody knows exactly what mathematical principle embodies. The idea here is that it's something like simplicity, we can think of it as the minus log posterior. Okay, so now what I want to do is kind of generalize this to a number of other problems in perceptual organization. So perceptual organization generally means aggregating visual elements into coherent forms. So far I've been talking about an individual coherent form, but the whole problem in general is you don't start by knowing what the forms are. You don't, for example, start by knowing what figure and round are. So we want to think about figure and round. If we have a whole image with many shapes in it, figure out what things are the shapes and which things are the backgrounds. That's the figure round problem. We want to group elements together to form coherent shapes and coherent objects and places and everything else in the visual image, etc. That's a much broader problem. So for us, it's a generalization of the way I've stated the problem. Instead of trying to explain the shape with a model, we're trying to explain the entire scene with a model which is a combination of individual object models. I should say, the shape literature historically just exclusively assumes that you have an object that has already been separated from its background, and it's just in an isolated field of white, typically. And that's a very hard problem, and we need to study that problem. But that's not actually, of course, how the visual system encounters these objects. It encounters them embedded in noise and occlusion and everything else. Some of the things we talked about this morning. So let me just start by talking about figure ground. So the model, as I've explained it to you so far, explains the shape data from the inside. We assumed it inside. What I mean is, if you're trying to explain this shape, we assume that the skeleton will explain it from the inside of the shape, and we assume that we know which side is the inside of the shape. That's, like I said, that's the traditional assumption. But what we want to do is assign a skeletal interpretation in such a way that it tells us which side is the inside of the shape. When I say the inside of the shape, that's what is meant by figure. So to see that, you have to put a couple of shapes into play. And so let me just say, here we have two shapes. I'm now just showing them as isolated edges. We have two shapes, but a priori, the system doesn't know what are the shapes and what is the background of the negative space between the shapes. Now, if you start a procedure similar to a simple generalization from what I showed you before, there's medial structure everywhere. So there's medial structure inside each shape. So again, each of these points is as a point of symmetry locally between edge elements that it can explain. But there's also symmetry structure in between the shapes, and that's partly an artifact of the way I drew them. But just to make the point, you could just as well think that this was the skeleton which would explain the near boundaries of the two shapes, but not the far boundaries of the two shapes. Of course, that's not the way it's perceived. So if you, however, if you take the maximum posterior, somewhere on the slide, we call it a multi-skeleton, a set of skeletons, what you find, as a slightly cherry-picked example, but what you find is that you can explain one of these shapes using the max posterior individual skeleton, then take it out of the shape, and then the rest is explained by another skeleton. In other words, this stuff all loses in competition with the stuff that was inside either one of the shapes. The procedure is a little more complicated than what I was describing before, but the idea is now we have ex posterior, a posteriori explain what is figure and what is ground, without really adding any new principles. And this I'll say kind of fast, but you could use the same probabilistic model to explain what is behind occluders. So this is work with Vicky Freund. So for example, in this one, once you've got the skeleton of the blue region, that provides a probabilistic prediction of where the edges are that you're not actually seeing, the ones that are included by the red region. And these red bands here give that so-called predictive distribution with some error, which is based on the underlying generative model. And of course, that is intuitively what you see. So in other words, you see these things completely straight behind, and that's what the model predicts. So that's what's called the posterior predictive distribution. So it's a side effect, again, without any really new principles. Okay, so this one is where it gets a little bit even more fancy. Same idea as figure ground, but now with occlusion. So here we have an edge configuration, and essentially we have a procedure which, this is a little bit aspirational because the procedure doesn't completely work yet, but I'll show you a slightly cherry-picked example. Or you basically do what I said before, you start with the skeleton that explains what it explains the best, remove it, and then continue to try to explain stuff that was behind, that is left after you remove it. And what you get in this example is you get a green shape that is a nearer depth plane. I mean, this removing part implies depth planes, because when you remove something, it implies that it was in front, you remove it, and whatever is explained and whatever remains then gets assigned to a farther depth plane. So here you end up with a shape in front of another shape, which I would say intuitively is what you see.
Can you give me an intuition for why it doesn't pick the two smaller shapes? Why doesn't one of the smaller shapes win out in the competition?
Oh, well,
So in the previous.
I'm not going to say they never do, because it doesn't totally work yet.
Okay.
But I mean, why not? It's because these data over here are very well explained by a very large model that has very low complexity or very high prior. Right? And so that's why the first thing that gets picked out is that entire region. These are relatively poor fits to any individual model, because it's not very axial. If this was elliptical and closed off relatively smoothly, then it might have won. But of course, then you might have seen it as a separate object.
But if for example I make those two rectangles,
Yeah.
then I think they would.
With the rectangles, yeah,
Yeah.
that's true. I've never actually tried it. I'm sure it would not work.
But wouldn't it be a rectangle missing one side?
Sorry?
Wouldn't it be a rectangle missing one side, because you gave that side to the first model?
If you
Doesn't it
picked
own the
out one of
border?
the sides of one of the rectangles on the side first,
Yeah.
then the rest wouldn't work. That's
Yeah.
what you mean.
No, I just mean that even if it were rectangular, the only contour you'd be left with, if I'm understanding how your competition is working, are 3 of the 4 sides
Yeah,
of each
right.
of those
No, that's right.
rectangles.
And then the whole thing would
You
work.
wouldn't have the whole thing. So, yeah.
Right, but I mean, then you'd have a terrible solution for the rest of it.
Yeah.
So, okay, so now I want to extend this to 3D a little bit. And again, the idea, 3D is a very hard problem. I don't mean to suggest solve it, but the idea is that you can approach it with a very minimal modification of the likelihood model. So instead of having a model where the axes generate skeletal structure, generate shape to the side, it generates it all around in 3 dimensions, like this diagram indicates. And that's what we call inflation. So you start with a skeleton in 3 space, and then you have this inflated thing which turns into a whole inflated shape. So that's in the forward direction is very straightforward. Of course, the inverse direction is harder, and what I'm going to show you is a kind of partial solution for a part of the problem, of the inverse problem, not really the whole thing. So this I'm going to say very, very quickly. But basically, Seha Kim, in a PhD thesis a few years ago, was able to invert our skeletal model using a sort of slightly ad hoc procedure for figuring out which elements now it's line drawings that include T-junctions like this. So we have line drawings that look like this croissant, and not everything is exterior. Now some of the elements of the picture are interior boundaries, and you essentially match those to to inflated models and do a kind of ad hoc inverse procedure. And so the idea is you then can do something that is an estimate of the 3D surface shape. So so this is what you're seeing here are estimates of here is the easiest way to see it. These little arrows are estimated surface normals. So basically, I know it's hard to see the details here, but these things that are perceived as sort of a croissant shape are reconstructed. The maximum posterior surface interpretation is that they are essentially croissant shapes. So the cool part, though, is that in the 3D world, in the 3D literature, people usually assume, again, a deterministic process to sort of figure out what the 3D shape is. But here we're assuming a probabilistic process, which turns out to fit human data better. So what we did, I'll just briefly say the experiment, is we showed these croissant shapes, line drawings of them, and asked subjects for a series of pairs of points, like for pair number 1, which dot, this open one or closed one, they're different colors in the experiment, was closer, which is a way of estimating what they think the 3D shape is. And so over on 5, people are very, very, very likely to say that the black one, the filled one, is closer than the unfilled one, right? Because it's clear given the implied 3D shape. I should say, to be clear, nobody knows in what way this line drawing implies that 3D shape. That's the problem. Over here, people will also say that the filled one is closer than the unfilled one, but it's a much weaker inference, much weaker judgment. People say that, but only by a little bit. So we were interested in modeling not just what they thought was closer, but to what degree they were confident that it was closer, because the whole thing is a probabilistic model and can predict that. So, so basically, if you look at the lower graph here, this is the fit between the data, which is in black, and the model prediction, which is in red. So the top row is with a uniform prior, which is not the prior that we concluded was correct. And the bottom row is with a prior that was, honestly, a little bit ad hoc because it's sort of motivated by findings in the literature. It's not necessarily motivatable on pure a priori grounds. But when you introduce that prior, it fits the data pretty well. Again, what that means is that the probability that someone will say that this point is closer than this point, that's what you're seeing on the y-axis here, is can be estimated from this 3D reconstruction along with the posterior strength of belief in the 3D depth that the model conveys. Okay, so I know I said that really fast, but the other significance of this, before I drop it, is there are 2 line drawings which I know look quite similar, but they're critically different because in this one, this curves this way, and this one, this curves this way. And believe it or not, that difference is critical in the shape literature, the 3D shape literature, because this one is actually not physically consistent with the applied croissant, and this one is. And Jan Kundrich showed this years ago, and people don't generally see the difference. And our data supports the idea that people don't generally see the difference. From a purely physical model point of view, this one is actually impossible. It's not, it can't be a projection of the shape that we're all seeing. Okay, so the last topic I want to just approach is shape similarity. So we have a model of a shape, and we have a model of another shape, and we want to say something about how similar the 2 shapes are, and it's natural to ask whether the models can help us answer that question. So let me just very broadly say that similarity is a very difficult problem. This morning we were talking about exact equivalence when an object is transformed in some way. But similarity often involves 2 things that are not exactly the same, and the question is, do the differences matter, or how much do they matter to a human subject? That's what I mean by the subjective. So if I were to ask you how similar these 2 shapes are, there's no right or wrong answer to that. They're sort of similar and sort of dissimilar. Some people might find them more similar than others. There is no mathematical definition for similarity. And of course, this is critical for the problem of shape matching, which is kind of underlying all of shape representation work, is the interest in how people actually decide what shape something is, what category it belongs to. So if I said, for example, this is a blicket, which is, this is a famous nonsense word from the child word learning literature. We now use blickets in our experiments for the same reason. We have an experiment like this, which I'm not going to show you data from, but if I say this is a blicket, and I ask you, is this also a blicket? You are going to answer based on your judgment of shape similarity, and it's not really clear what the right answer is. There is a huge literature on cognitive similarity in the broader problem beyond just shape. It's not super helpful. There are a lot of models that are based on the idea of mental distance between points in some mental space, but in the question in shape, as I started by saying in the very first slide, the question is, what is the shape space? What are the properties? What are the features of that space? Once we have that question, we can say there's distance in that space, but we don't know what space we're in. And similarly, there's a lot of work in cognition about similarity based on features, meaning like you could say two things are similar to the extent that they have the same features or don't have a lot of distinctive features, but that begs the question, which is what are the features of shape that we care about? So I'm not saying either of these are wrong. In the cognitive literature, they're usually considered to be opposed ideas. But in any case, I'm just saying that both of those don't really answer the key question that we want. So, so what we try to do is to take the skeletal modeling of shape and find an appropriate way to think about similarity. So traditional measures of similarity, there are many, many measures of similarity related to the many approaches to shape representation that I talked about at the beginning. Most of them historically are geometric, meaning you make up some kind of mathematical property of the shape and then ask whether the two shapes have similar value with that property. And there's no stochastic element or no degree of belief element in modeling. So there are some measures, I should say, that are skeletal. So there's a lot of work in basically you have some sort of tree structure like a skeleton, like I've been talking about, that represents one shape and the other shape, and then you try to match the two trees. There's a huge literature on graph theory on graph matching that can help give you some concrete algorithms for figuring out whether two skeletal structures match. But there's no probabilities associated with this for the most part. What we want to do is to think about this problem fresh and to ask what we're actually asking when we ask whether two shapes are similar. So I don't make this too grandiose, but the question is, what does similarity actually mean? And our answer is similarity is evidence in favor of a common model. Meaning you're asking whether the two objects in general, let's say two shapes, whether they appear to have been generated by the same process. If they do, then you think they're the same process. And the greater the probability you think they are the same process, the more similar they are. So that can be reduced to something called the Bayes factor, and this idea is due to Josh Tenenbaum and collaborators years ago, but not in the realm of shape, in the realm of other things. So basically what we're saying is that the similarity between two shapes, A and B, is going to be proportional to the log of the ratio between their likelihood, the two shapes is likelihood under a common model, relative to the two shapes' likelihood under two distinct models. So cap A is a model of little a, and cap B is a model of little b, and cap C is a common model. I'll explain what that means in a minute. And the question is, how strongly do we believe the common model relative to the two distinct models? And if that's high, then we think the two are similar. The idea is this is sort of just a priori, a good way to think about similarity. So what I then just need to explain is what a common model is. So to answer that, we have this thing we think called the skeletal lattice, which is essentially just a set of possible topologies of skeletons. So these are not for any real shapes, these are just topologies of skeletons. So at the top you have the simplest possible skeleton, which is a single axis. Then it can branch once, and then it can branch again in two different ways, and et cetera, it can branch again in various ways. And so if you go infinitely down to the bottom, infinitely down through the floor, you can get any possible skeletal structure. And so it goes on forever. So the idea is that at the top we have simpler topologies, and at the bottom we have more complex topologies. Of course, the prior that I was talking about starts high at the top and goes lower, lower, lower as you go down. So with that in mind, start with two shapes, A and B, as I said before. They have different structure, they have different modelings. So we're now going to estimate their skeletons. These are the map skeletons for them. Consider just the topologies. Graphic here. Just consider the topologies of the two skeletons, and then look at the join, the lattice join on the shape lattice. So the lattice join is the least common model, the model that is above both of them. And in a lattice of nodes like this, there's always guaranteed to be one common element above and also one common element below. We're going to look at the one above. And you can think about the pathway between this skeleton and this skeleton as passing through this common model. So basically the numerator of that Bayes factor that I mentioned before, the probability of the common model, is proportional to the product. So I'm skipping a few details here. The product of the probability of the shape A, which is gone here, conditioned on this skeleton, times the probability of this skeleton given this skeleton, so there's some probability cost, with adding a branch, which is what we did. We went from C to A, times the same probability for going from B to C, and there was a probability cost associated with adding branch a different way. One way it's adding branch, one way it's removing a branch. Now we assume that the probability of adding branch and removing a branch are the same, which is a simplifying assumption. That means we can invert one of those arrows, and so I'm cheating here by inverting one of these likelihoods, and then we have the probability of the final shape B given the skeleton for it. So I know there was a long chain here, but it's basically a way of saying what is the probability of going from this shape through its model, through the common model, to its model, back to the other shape. And the math just follows, the equation just follows that path. So if you take the minus log of that probability, as I said before, you get the description length of the path length from this shape to this shape. And that's what we think of as the similarity. So, so to give you some kind of concrete examples, this is, I should say, it's work in progress, and we have some data in support of this, and I'm going to show you some old data in support of similar models, but I'm not playing this necessarily right because we're still tuning it up. Basically, when you have two shapes, these are hand-drawn blobs, they're obviously different from each other, but they're I would say intuitively pretty similar shapes. So the DL is a very low number. It's actually below 0 because there's some figuring with the constants. Then when you change it to be another shape, there's the two that I started with, the DL is much larger. So larger DL means a lower probability. So that, in other words, there's a greater distance, probabilistically speaking, from that shape to that shape. And if you change it to something even really different, then the DL is very much larger. And then a few just examples of animals. So these two fish are different from each other. That's a relatively high number, I should say. The numbers generally get higher the more complex the shapes are. It's very hard to normalize for that. But compared to other ones, so like the DL between a fish and a dog is much larger. This is a log space, so the difference of a few units is a big difference in the ratio of the probabilities. And between this fish and this cat is also very high, and I'm just throwing a few other examples like that. Fish is more different from that cat than that fish is from that cat. I mean, that I can't speak to in detail whether it's empirically right. We're doing experiments right now. I do have data for an earlier generation of this theory, so I don't want to make it sound like it's exactly the same theory, but it's a theory in a very similar spirit where we actually did compare it to human psychics data. And so basically here, very briefly, we asked subjects for similarity ratings among a whole bunch of shapes. These shapes are all very similar to each other, but they do vary in topology from simple one-axis shapes to shapes with an extra part, with a whole narrow range in between. And the computed similarity versus the human similarity is a nice straight line. Here we have a bunch of more complex shapes with all the same topology but different shapes within that topological class. And again, we get a nice linear correlation. And here we have some shapes which we chose to be particularly non-axial. They weren't generated by any procedure similar to our forward model, just to see how robust the model is. And there you get, it's a much larger set than what I showed here. There you get a nice correlation, although you can see some nonlinearity here, which we don't have an explanation for, so it's clearly not the whole story. Let me show you a little bit more data, again, with a slightly different similarity model, mathematically related to what I proposed with a slightly older generation. In this one, experiments were asked just to perform discrimination tasks on two very similar shapes. And what we were interested in, this big picture, is their ability to discriminate two shapes as a function of the similarity between those two shapes. In other words, people could discriminate some shapes from each other more easily than others, and the question is, could we explain those differences by this model of shape similarity? So what I'm going to be plotting is the one over the threshold for discriminating a difference between two shapes. And you can see the shapes themselves on the x-axis here. So I just wanted to relate this back to what we were talking about this morning with invariances and symmetries. We chose this is a shape morph space between a circle and an ellipse, and we chose that, and a few other things I'm not showing you, because we were interested in what happens when you break the symmetry, the rotational symmetry of the circle, and you end up with an ellipse, which still has some symmetries, but it's missing one symmetry, the rotational one. And but we don't use that directly. We just use the shape similarity procedure, like I said, an earlier generation of the one I told you about. And you find that people are more sensitive, one over threshold is higher, when they deviate from a circle by a small amount, and their sensitivity is getting lower and lower as it goes more to the ellipse. In other words, the subjective difference between this ellipse and this ellipse is smaller than between this circle and this slightly modified ellipse, etc. And I'll show you just a few more examples. We do this with many shape families, many morphs. So here it's sort of between a two-part shape and a three-part shape, and subjects have the greatest sensitivity and somewhere at the boundary between two kind of qualitative classes here. Again, this is sort of a randomly generated growth space. We didn't know exactly what to predict, but the model predicts something. But again, the black is the model. The colored data are individual subjects. So there's a lot of agreement between subjects here. Not always, again, cherry pick data, it's not always this much agreement between subjects. But again, here's another one with a circle and ellipse with slightly different conditions of display, and another with 2 parts versus 3 parts, a different random shape. So you can see it often works pretty well, and it's a little mysterious. We don't exactly. There's nothing in the theory that says that breaking symmetries is going to be hard for subjects to handle, but that's what the theory says. Okay, so that was a lot of topics in shape representation, just very, very breezy and very fast, I know. But let me just say that the problem of shape is just part of the problem of perceptual organization. Right? So I think it's a mistake to isolate shape as a separate problem from all the others. There sort of has to be some commonality. It doesn't have to be imagined for scientific parsimony. There's some commonality among them. The idea here is that we think of them as more and more complex sets of generative models and a common inference procedure. So this is what I mean by a common rational framework. And the term rational is sort of a buzzword for Bayesian models, but what I mean is that the inference that the subject is making, the observer is making, sort of makes sense. Given them the model of the world that they've assumed, the organizational grouping that they prefer makes sense, makes the most sense possible given their assumptions. So all you need is an appropriate generative model, which, let me say, the skeletal model that I'm describing is just a very particular set of assumptions about how shapes are generated. It's not really supposed to be the model. A lot of it is somewhat arbitrary. But the point is the whole framework can be ported to slightly more sophisticated or even qualitatively different models of real shapes. So all of this is a little bit pie in the sky as far as what kind of shapes we're looking at. The idea is to look at more naturalistic shapes that might have more complex models. But once you couple the generative model with a set of tractable estimation procedures, the idea is something like reducing a whole set of problems that the Gestalt has looked at to just essentially instances of Bayes' rule. Just once you have the appropriate model, estimate the model, and that's what you see.
Time for 2 or 3 questions.
So this is beautiful stuff and continues to be beautiful. But as I was sitting here, it struck me as I looked at some of your examples how believable some of them looked and how some of them looked out. You could never see that. It made me think that there must be a limit to how far you can go with a purely rational model, and at some point you've got to get the prior from empirical research on the natural world, which is what I think people must be basing things on, right? They know how things grow biologically, they know how things are constructed, artifactual.
I don't know where to begin.
Okay, sorry.
I don't actually agree that people get the prior from the natural world.
Huh.
But on the other hand, I do agree that this is kind of the simplest, most vanilla case. And to tune this to the world, you need to complicate the model substantially and inform the prior in a much more interesting way. So, I mean, some of us in the hallways have been talking today about the issue that Sam and I were talking before, about how how much of the prior can be motivated just based on kind of the empirical structure of shapes in the real world versus on sort of pure mathematical principles. And that is a really difficult question, which we can debate for days. So what I was saying about circles versus ellipses is supposed to touch on that a little bit, meaning that suggests that it goes somewhat in the direction of breaking symmetries helps inform the prior, which the point is independent of empirical data in the world. But on the other hand, you would expect empirical data in the world to agree with those kind of mathematical regularities for various reasons. But the interaction between those two is super complicated topic. I mean, there is a whole tradition in the Bayesian literature of choosing priors based on invariances. In modern cognitive science, we often we are told we're supposed to choose the prior based on natural image databases, and that's not actually how people do it in the traditional Bayesian literature. How it actually works in cognitive science, like the brain, is somewhere in between in some way that we don't, I certainly don't fully understand.
I just had a question kind of because I've been grappling with similar things, and that is, where in the visual system do you think this is all happening? I'm not necessarily talking about neurally, but just if you start from early vision to very high level vision, I would assume the figure ground sort of stuff is happening fairly early in image analysis, where you're trying to identify surfaces and separate objects from backgrounds. And then the shape skeletons for the objects, is that also like fairly early?
I could only give you the most speculative answer, but
Yeah,
let me say a
sure.
couple of things. So, I mean, there are these recurrent connections. I'm certainly not the person to ask about what they're doing, but it's they're recurring, meaning backward pointing projection, forward pointing brain. That where more high level form information is influencing things that we usually think of as lower level, like figure ground. Figure ground is usually thought of as an earlier process, but it doesn't necessarily need to be if it's informed after the first 50 milliseconds by later processes. But so let me give you a completely different answer to your question. So, like I emphasized before that we're not computing curvature, but like Anita just gave us to talk about what curvature is computed, and I don't find that implausible at all. That these are different levels of analysis. So, meaning that that if you wanted to implement this estimation procedure in a brain, in an actual neural network, it might be that the best way to do it would be by putting in some kind of curvature-based population code, similar to what Anita had proposed. So, I mean, to me, those are actually consonant proposals. I mean, I don't actually know that this estimation procedure would lead to that population code. I don't know if they're consistent, but they certainly could be consistent. So all of this is a way of saying, if you want to know how it's actually implemented in the brain, go talk to them. But I mean, if we're actually computing curvature, that doesn't conflict in my mind with what I'm claiming, which is various sort of computational theory, not implementation.
One more minute. Sorry.
I was just wondering if you'd applied this method to Canesius triangle or any other common optical illusions and seen if it evolved the same way. That would be an interesting test.
Yeah, no, I mean, no, we haven't. I mean, this is done at the level of the way I described it. It's taking as input edges, and in order to do something like this triangle, you'd have to have a recurrent, some kind of recurrent application of information from something like a triangle that you estimated down to the edges that you've hallucinated. And there's nothing like that in this theory, but that's a great direction to extend it. I mean, one of the things that I would like to do is to try to implement this in some sort of a neural network in order to get to the implementation level that I just said we're not at. And then you might have a prediction in that direction. That's total speculation.
All right, we'll save Liz's question for the break. Thank you again. We'll resume at 4 o'clock. I don't see sound yet.
So your lecture brought back a fond memory I have of listening to Seymour